And thanks to Professor Panigrahi and all the organizers of the summer school for inviting me. So I listened to some of the talks in the summer school, and earlier there was couple of very interesting talks by Professor Michael Hall and Professor Archan S. Majumdar in the summer school, which introduced us to the concept of Bell non-locality. And later on, I think there will be another talk by Professor Guruprasad Kaur, which will be focused on Bell non-locality, and we will get more opportunity to learn about this interesting topic, which is interesting both from foundational perspective on quantum mechanics and as well as applications to quantum information processing. So, as you can see, the title of my talk is Communication Cost for Simulating Bell Non-Locality. So, this talk is mainly prepared with focus on younger researchers. So after reintroducing the concept of Bell non-locality, I'll try to define the problem in the title of this talk, and then try to illustrate this problem with some concrete examples. Uh, Along the way, I'll also highlight some open problem on this quite interesting topic. I hope you find it interesting. So, yeah, so my first slide is something about quantum statistics. So as we all know, that quantum mechanics allows us to share a single quantum state between two parties or more parties, of course. But here, for simplicity, we are just considering two parties, and we are calling them Alice and Bob. And this is the shared quantum state, say psi AB. And on her and of course Alice and Bob can be located in faraway locations, and suppose Alice performs a measurement X on her part and obtains an outcome A, and Bob performs a measurement Y on his part and obtains an outcome B. Then we know that from quantum mechanics we can calculate the probability of getting outcome AB when the measurement was X and Y using the Born rule. So quantum mechanically, we can just compute this probability of outcomes given the measurement from Born rule. So now I'm just trying to introduce the idea of Bell non-locality. So this is all about quantum description of this probability. But one can ask question like, can there be a more fine or complete description of quantum probability? In my next slide, I will try to explain what do we mean by more complete or more fine description of quantum probabilities. So, and then here comes the notion of hidden variables. So basically, different kind of hidden variable models for quantum probabilities try to understand the quantum mechanical correlation more deeply. Uh, so, so here generally one consider that there is a hidden variable lambda. If we knew that, we could describe, we can get a more, we can get a better description of quantum probabilities. So, and in that case, if the hidden state lambda is known, then the actual, the more fine description of the outcomes would be like probability of getting outcome AB when measurements are given and the hidden variable lambda is given. And what we operationally observe or see in the experiments or the quantum mechanical description of probability is basically averaged effect over all the hidden variables lambda. So hidden variable lambdas are hidden, that's why we see as an average effect these experimental or quantum mechanical probability. So this is the general idea of hidden variables. So in general, here we don't assign any physical attribute to our hidden variables, and in that case, we can just write quantum probabilities as this kind of decomposition, which is basically a statement of Bayes rule for probabilities. So, but it becomes interesting when we try to give some physical attributes to the hidden variable. And perhaps the most interesting one is that saying that the hidden variable we assume obey local realism, or the hidden variable we assume are actually local hidden variable. So by this, it means three things. The first one says that the state of the system lambda is not correlated with the measurement. So what measurement I perform is uncorrelated on the state is uncorrelated with the state of the system. So this is a free will assumption, or also called like measurement independent assumption. Uh, and then there is this locality assumption, or sometimes also called parameter independence assumption. And it says that probability that Alice gets an outcome A should not depend on what measurement Bob is performing. So the probability of outcome of Alice should only depend on the local measurement and the local hidden variable lambda. And similarly for Bob. And this assumption of realism or determinism says that if one knows lambda, actually there are no probabilities. So outcomes of Alice and Bob are completely determined. Either it's probability of any outcome is either 0 or 1. So it is deterministic. So if we give these assumptions to our hidden, these physical attributes to our hidden variable, then the question is whether all quantum probabilities can be written in this way, or can it be decomposed in this way? So this was the question from where Bell inequalities emerge. So actually, in fact, what is the statement of Bell's theorem is that it is not true. Like if our hidden variables are local hidden variables, in the sense like they satisfy all the three physical assumptions described in previous slide, then they can't be always decomposed in this form. So they can't be written in this form. So yeah, so this is the Bell's. So how do we show this is basically, if we take these three assumptions, one can go and derive that if hidden variables are local hidden variables, then the correlation, the experimentally observed correlation function must satisfy Bell CHSH inequality, which is nothing but bound on a function of correlations. So according to local hidden variable, if some correlation satisfies local hidden variable, it must this function must be bounded by 2. So yeah, so the whole thing is started with whether there can be a local hidden variable description of quantum statistics. But then one immediately sees that if one shares entangled state, for example, a singlet state, and Alice and Bob chooses the measurement as follows, the quantum measurements as follows, then the probability distribution one get on measurement XY outcome AB of this form where alpha is this number, 0.43, beta is this number. And when we compute the value of del CHSA expression, it is 2 square root of 2, which clearly violates the bound arising from assuming local hidden variables. So, so, so quantum mechanics violate Bell CHSH inequality, and therefore it cannot be the quantum correlations or quantum statistics cannot be described uh, by a finer local hidden variable model. So now I come to the main subject of my talk with this background. So now the question is, so from the violation of Bell theorem, one can conclude that if one assumes that measurement independence hold true, then the assumption of measurement independence is true, then some communication is necessary for simulating quantum statistics. So, which means that now if we want to simulate the quantum statistics in all possible way, we will need to have some communication between Alice and Bob. Otherwise, it can't be possible. Now, this topic of study comes both from the foundational perspective and also to study the strength of entanglement as a resource. So it's also like helps us to understand the quantum, the resource entanglement in quantum information, like in terms of these communication tasks. So the question is that what is the minimum necessary communication that one would need to simulate Bell non-local correlations? So generally in this problem there are two types of problem, like two types of formulation. So now the question is, if we are given a state rho AB, type 1 problem says that tries to construct a low cost or optimal C-bit protocol which works for all measurements X and Y. So the measurements can be arbitrary, but there is just one protocol which will tell us that whatever measurement Alice and Bob gets, they can simulate the quantum probabilities by certain number of C-bit communication. On the other hand, the type 2 protocol restricts the measurement set. So here one tries to simulate the quantum probabilities, Bell non-local quantum probabilities, when measurement, the set of measurement is defined and it is finite. So here now we have like only a finite set of measurement from which Alice gets 1 and Bob gets 1, and as a result whatever statistics one can generate, goal is to simulate with C-bit protocol. So one can note here that solution of type 1 problem is always a solution of type 2 problem, because in type 1 problem the protocols simulate arbitrary measurements, and here protocols simulate measurements from a given finite set. So let me first discuss about the type 1 problems. So as an example of type 1 problem, a concrete example, it can be following. Suppose Alice and Bob, so if Alice and Bob shared a maximally entangled state, singlet state, and Alice measures in some direction X and Bob measures in some direction Y, then for singlet state, one can, using Born's rule, one can calculate that the quantum probability can be written as follows. So like this equation. So the probability of getting outcome A and B when measurement is X and Y is given by this quantity. So now the problem is for arbitrary measurement direction X and Y, how can one simulate quantum statistics with minimum possible communication? So this problem has interesting history, and like there were many series of attempts, but I would here mention just two key papers. One paper was by initially in 1999 by Brassard, Clave, and Tapp, cost of exactly simulating quantum entanglement with classical communication. And they showed that with 8-bit of communication, they give a protocol in which if 8-bit is communicated from Alice to Bob, and Alice and Bob have some pre-shared randomness, then it is sufficient to simulate the statistics of singlet correlation. And then there were many attempts to reduce this communication cost, but then there was a big jump and very interesting, surprising result by Toner and Bacon in 2003, where they showed that just 1 bit of communication from Alice and Bob and pre-shared randomness is sufficient for simulating the correlation generated by maximally entangled state of 2 qubit. So it was good if I had put some figure, but just let me try to go through the protocol. So, and this can be a very interesting exercise for young researchers, because like understanding this protocol. So so the protocol goes like this: that Alice and Bob pre-share a lambda, which is basically a pair of unit vectors, and they are in R3, which are uniformly distributed on a unit sphere, and lambda 2 are independent. So I can just mention the steps of the protocol, and just noticing that so Alice has first, so they pre-share this randomness. So basically these are 2 vectors on a sphere which they pre-share. So now Alice has to give outcome when he gets a measurement X, she gets a measurement X. So she gives outcome as the minus of sign of the measurement direction she gets and the lambda 1 vector what she has, which she shares also with Bob. Now Alice to Bob, she sends a C bit according to following a rule. So basically it's sign function of her measurement direction and the first random variable shared, and then her measurement direction and her second random vector which she shares with Bob. Now Bob gives the outcome as follows. It's a sign function of measurement he gets and lambda 1 and lambda 2 which he shares with Alice, and this communication bit which he received from Alice. So this protocol as such looks simple, but it involves a bit of tricky calculations and involved calculations. And I forgot to just mention that this is sign function. So if the this Z is greater than 0, it is +1. If otherwise, it is -1. So just few things I want to mention, that at every step, one can note that this is a deterministic protocol. So for any given measurement, Alice is given, she will give a definite answer, either 0 or 1. And similarly for Bob, he will give a definite answer, either 0 or 1, or +1 or -1. So with this protocol, if one do the calculations, and then the goal is see that one need to calculate from the protocol this conditional probability, and which is this integration of this over lambdas, the shared hidden variables or shared randomness. So, and some simple things equivalently, one can also show that the expectation of this measurement of Alice is 0 in this protocol, what I discussed above. Expectation of measurement Y is 0, which should be for singlet state correlations, and expectation of this is -x dot y. So one can also prove this, or one can prove this, to show that model really simulates the singlet state statistics. So this one can take as a very interesting exercise, especially for younger students, and to really appreciate this protocol. Now, in the same paper, Toner-Bacon also showed what if the state they take is any arbitrary state in C2 tensor C2. So, so here they used or a little bit modified a protocol by Surf, Gissin, and Massar, where they showed that Alice can prepare and classically teleport to Bob by state row belonging to CT by using shared randomness and 2 C bits. So in this case also, they give a protocol for this simulation. So Alice can output plus or minus 1 with probability given by this, and determine the post-measurement state rho B of Bob. So once she determines the post-state measurement state rho B of Bob, Alice can teleport rho AB to Bob using 2 C bit and shared randomness. Now Bob will perform measurement Y on rho B and declares outcome as his output. So this is a protocol which, using 2 C bit, can simulate not just singlet state statistics, but any state from C2 tensor C2. So this is one protocol, and one still doesn't know that if this protocol is optimal protocol. So this is still open. So the few other known results on type 1 problem I mentioned here. One paper is by Regev and Toner in Siam Journal of Computing, where they show that 2 outcome projective measurement on any state from CD tensor CD can be simulated by 2 C bit and shared randomness. So they show that even if the local Hilbert spaces are d-dimensional, just 2 C bit is, along with shared randomness, is enough to simulate the quantum statistics of such states. And then there is another result by Wartzi and Bene, where they say that for perfect simulation of 2 outcome projective measurement on a maximally entangled state, here 2 C bit communication is necessary. So what they say is that in CD cross CD, if one wants to simulate maximally entangled state, then one cannot do with less than 2 C bit communication. So yeah, so just to summarize, the key paper in this type, I would say, is the paper by Toner and Bacon in 2003, Communication Cost of Simulating Bell Correlation, and project uh, and it considered projective measurements of this type by Alice and Bob, and it gives one C-bit model of type 1. Type 1, I again just repeat that type 1, we mean that it can simulate arbitrary many from any for any possible choice of X and B. So there is no restriction on what measurement Alice and Bob would be asked to perform or will get. So, so there is a 1 C-bit model for maximally entangled state and 2 C-bit model of type 1 for any 2-qubit state. Now, the open problem is still like it looks so simple, but it's open for problem for long now. That is there some 1 C-bit model of type 1 for all row A, B, C2 tensor C2. So this neither till now, neither one could give an explicit model of 1 C-bit or between uh, uh, or neither one could give a counter example. So the actually the type 2 problem was I think it was motivated among other things. One of the also motivation which type 2 problem which I'm going to discuss next is also one of the motivation is to see if there are some counter examples to this problem. That so we will see how. So now I'll discuss type 2 problems. Uh, so here again the problem is same, like Alice and Bob may share some entangled state or share some state, and then they have measurement outcomes. But now the measurement Alice has is restricted to a finite set. So Alice will not be asked to simulate all measurement from the protocol, but only the measurement from this finite set. And similarly for Bob. So the measurements are now restricted to finite many possibilities. And now the problem is to simulate these statistics for a given state psi AB, to simulate these statistics by optimal communication protocols. So one can just notice that these are fixed bell scenarios, because in fixed bell scenarios we always specify the number of measurement from which Alice chooses, and similar and number of outcome for each measurement, and similarly for Bob. So this definition of the problem correspond to a fixed bell scenario where number of measurement and outcomes and parties, they are specified. So this was again like the first idea on these type 2 problems was again by paper by the same author, Bacon and Toner in 2003. And what they did is that they they come up with this concept, Bell inequalities with auxiliary communication. So they come up with this idea that if we allow a limited amount of communication
I think you have to unmute yourself.
Yeah. Sorry. So
Okay, we can see your slides.
okay. Thanks. Sorry. I somehow maybe I
Yeah,
lost.
it's okay. It's okay.
Okay. So yeah, I uh, if if I was on here, then I already discussed type 1 problem, and I was discussing type 2 problem for simulating quantum statistics. So yeah, so here we have same like Alice and Bob can share a state entangled, or and but the measurement choice they have is finite. So these correspond to fixed Bell scenarios. So yeah, so then for this type 2 problems also, like again Toner and Bacon came up with idea of Bell inequalities with auxiliary communication. So they theorize this thing, like basically if they consider that if one allows some C-bit communication from Alice to Bob, then they can derive a new kind of Bell inequalities. And if some correlation would violate that Bell inequality, it would mean that that correlation cannot be simulated by uh, the the number of bit of communication used to derive that Bell inequality. So that if the correlation violate auxiliary Bell this kind of Bell inequality, then with the auxiliary communication, it won't be possible to simulate that correlation. So uh, and they first consider these simple cases when number of measurement choice for Alice and Bob is either 2 or 3, and outcome for each measurement is 2, and they solve this case for x equal to when x equal to y equal to 2, then they solve this fully. So by solving this fully, I mean that if one goes into details of this, then by solving it fully means they exactly knew all the Bell inequalities for this scenario. I mean all the Bell inequalities with auxiliary communication for this scenario. And for when measurement choice is x and y equal to 3, then they could only partially solve. So one more point I want to mention is that by fully solving also, like if we remember the conjecture that can any 2-qubit state be simulated with less than 2 bit of communication. So what they showed that all the auxiliary Bell inequality derived in this scenario, what they showed that all the 2-qubit state satisfy these Bell inequalities, which means that with this scenario, they can't mm, uh, they can't answer the question whether it can be simulated with one C-bit of communication or not. So basically, here we have two parties, Alice and Bob, and certain bit of communication C, and this is the setting for deriving auxiliary Bell inequalities with auxiliary communication. The usual or standard Bell inequalities, they gives bound on local hidden variables. So if we recall in the derivation or in usual Bell inequalities, no communication was allowed between Alice and Bob. So C was 0. So if there is no communication allowed between Alice and Bob, then what one derive is standard Bell inequalities. In case of Bell inequalities with auxiliary communication, one allows some communication from Alice and Bob. And then one asks the question, what is the correlation allowed under these new setting? So basically, these auxiliary Bell inequalities basically gives bound on communication models. So bound on LHV model when C is equal to 0. So one usually computes all the deterministic functions from Alice to Bob, and then tries to solve in the probability space, so basically all these conditions are linear. So in the probability space, generally one gets a polytope which determine these Bell inequalities. So basically tries to solve this problem in general for deriving Bell inequalities as such when there is no communication. And then of course the Bell inequalities are facets of these polytopes. And when one allows some communication like C greater than 0, then one can consider for such model, one can define so in this case, for example, when communication is allowed, like the outcome of Alice can be function of both measurement of Alice as well as Bob, because this communication may carry some information of measurement of other party. So in general, when there was no communication, that is when we derive the standard Bell inequalities, then we cannot have this kind of dependence. So outcome of Alice will only depend on measurement of Alice and shared randomness. But when one tries to derive this Bell inequality with auxiliary communication, one has to also deal with this kind of dependencies. So as we see that now this function will depend on allowed communication. So same as how we derive Bell inequalities, here also we try to find all the deterministic strategies. By deterministic, I mean that for a known xi, yj, and lambda, this outcome should take a definite value. So in this case also, one gets a polytope, and Bell inequality with auxiliary communications are basically facets of this polytope. So now this one can see that in some sense to have this communication models or auxiliary communication Bell inequality, there should be some restriction on C, otherwise they can become trivial. For example, if Alice and Bob can communicate log x, like number of measurement Alice has, or this bit, then all these functions become accessible, and so this is trivial. So one can understand this, that Alice or Bob should not be allowed amount of communication which can transfer all the information about their measurement. So if, for example, if Alice is allowed to send this much bit, then basically she's sending in each run which measurement she is performing. So then it becomes trivial. So usually the limit on the communication C is set by these quantities. So this is, and also like it's known that in quantum mechanics respect no signaling principle. It also respect one-way no signaling principle. So if Alice can communicate this much bit to Bob, they can simulate any quantum correlation. So just without any loss, like one can just consider that goal is to simulate quantum correlation only by considering one-way communication from Alice to Bob. It is sufficient. So we saw that there is a natural, interesting for these Bell inequalities with auxiliary communication to be interesting. This C should be greater than 0, but less than log of number of measurement setting of Alice. Then one tries to compute all the deterministic function like this that are accessible with C-bit communication. So these are the, so if this number of C-bit is allowed, then one tries to compute all the deterministic function. So now here is the detail of how one do this calculation. So it will be interesting to go, maybe not now, but the details of calculation one can look in the paper to understand this. So now I just go with some of the results which has been derived. So when in this scenario, like there is this number of measurement of Alice and Bob, and outcome for each measurement is just 2. And then the communication allowed is just 1 bit. So then this is called auxiliary Bell inequality of type the number of measurement setting of Alice and Bob is mentioned, plus 1 means 1 C-bit of communication is allowed from Alice to Bob. And as I mentioned before, the motivation for deriving this Bell inequality is to try to answer this question. Is there a 2-qubit quantum state which cannot be simulated with 1 C-bit communication? So to find an example of 2-qubit quantum state which cannot be simulated with 1 C-bit of communication. So if with any 2-qubit quantum state one get violation of this auxiliary Bell inequality, then it would mean that that particular 2-qubit quantum state cannot be simulated by 1 C-bit communication. So here it's just steps in derivation, but these are the steps like how to derive this Bell inequality with 1 C-bit communication. But in this direction, I will just mention some key results and key results in this direction. So in the initial paper by Bacon and Toner, they solved this when Alice's measurement setting is 2, Bob is 2, and 1 C-bit from Alice to Bob is allowed. When Alice is 3 and 3 and 1 C-bit. So here itself, like problem becomes so complicated, like geometrically, mathematically, that this answer is partial. So they could not completely rule out all 2-qubit state, they could not completely rule out that there is no 2-qubit state which can violate this kind of Bell inequalities. And here they solved complete means that they showed that there are no 2-qubit state which violate this type of auxiliary Bell inequalities. And there is another paper by Maxwell and Chitambar in 2014 where they solve this case completely. Solve completely means they could answer that there are no 2-qubit state which violate this kind of auxiliary Bell inequalities.
Please unmute yourself.
Hello?
Yeah, now we can hear you.
So basically all this effort, but still there is no violation with any 2-qubit state so far. So whatever Bell inequalities with auxiliary communication has been derived till now by considering more number of settings.
Sorry, your screen is not visible.
Oh,
You need
my
to say.
share again.
Yeah.
Now is it visible now?
Now it is.
So I don't know where I lost the connection.
Yeah, we lost you for a few seconds.
Okay, then it's fine. So basically, I was discussing about Bell inequalities with auxiliary communication, and the motivation for was this conjecture, and the complexity of deriving these such Bell inequalities with increasing number of measurement settings grows very fast. So there has been like only studied up to this, but whatever it is studied till now, there is no violation with any 2-qubit state so far. So all the Bell inequalities auxiliary communication derived so far in this setting we are considering, none was violated for even one 2-qubit state. So on the other hand, if this keeps failing, one would expect that then maybe there is better than 2-qubit type 1 model for 2-qubit states. But here also, like this is also open. Like till now, no one has come up with 2-qubit type 1 model for all 2-qubit state. So yeah, so now after all these topic discussing, like at the same time, like just couple of years after Toner and Bacon result, there was a paper by Sarf, Gissin, Masar, and Popescu simulating maximal quantum entanglement without communication. So this may sound surprising that till now we were saying that communication is necessary to simulate statistics of any Bell non-local correlation. And now here is a paper which says that maximally entangled states, the statistics of generating from them can be simulated without communication. But let me just elaborate it. Yes, this is without communication, but the resource used in this paper or in this protocol uh, is a non-physical resource. That is, one cannot. This is a non-physical resource which goes by the name of Popescu Rolich box. So with this kind of pre-shared peer box, in that the author showed that no communication is needed. If we just have this hypothetical resource, one can simulate singlet state statistics. So let me just briefly describe this peer box, because this is a very interesting conceptual tool occurring again and again. So basically, it just says that Alice and Bob both have two inputs, 0 or 1, and each input has two outputs, 0 or 1. So it just says that if Alice and Bob's measurement are of the type 0, 0, 0, 1 or 1, 0, that is product of their measurement label in this case is 0. In all these three cases, it is 0. Then Alice's outcome is perfectly correlated with Bob outcome. So these are outcome probabilities. So there is half probability when they are correlated as 0, 0 and half when they are correlated as 1, 1. And similarly, in all other cases where product of their measurement is 0. And when product of the measurement is 1, then they are perfectly anti-correlated. So half probability to be anti-correlated in this way and half probability to be anti-correlated in this way. So with such, and one can show, like one can argue, and this can be also interesting thing to check, that these kind of correlations are not realizable in quantum mechanics. So basically this kind of correlation, they respect no signaling principle, but they are not, they cannot be achieved by quantum state and measurement. So they could simulate singlet statistics with this hypothetical correlation. But again, then since these are not physical, one can ask that then how much communication would be needed to simulate peer box. So I think I'm towards the end of my talk, and I will just show that 1 C-bit communication is necessary to simulate peer box. So in essence, like it seems like it does better than Toner and Bacon model, but actually if one really want to have this resource, one need again 1 C-bit of communication. So this is a like simple protocol where one can simulate this peer box correlation with 1 C-bit communication. So we suppose that Alice and Bob pre-shared randomness lambda. So basically, lambda is a list of 0 and 1 which are perfectly correlated and random, and one copy is with Alice and one copy is with Bob. Alice's outcome A is just lambda. So at any measurement she gets 0 or 1, she will answer with lambda in her list. And Alice communicates, 1 C-bit is in this protocol allowed. So Alice communicate just what was her measurement setting. And then for Bob, it is easy to answer B in this way. So when C is, for example, 0 and Y is 0, or C is 0 and Y is 1 and 1 and 0, in all these cases, this product is 0. So Bob answered just with lambda. So in all these three cases, he will be perfectly correlated with Alice's bit. And when C is 1 and Y is also 1, he has to just flip his bit. So basically this becomes 1 and lambda is flipped. So we can see from the previous. So basically it says that when Alice communicates her measurement setting to Bob, then they can simulate this correlation, but one C-bit will be needed. Now, one may ask, like, is this protocol optimal, or can one do better? So can one do this simulation with less than one C-bit? So if one can argue that no, it is not possible to do with less than one C-bit. So yeah, so basically, yeah, so now, like, I just want to summarize my talk. So we see that there are other simulation models instead of C-bit, which consider hypothetical non-local correlation like peer box, or as Professor Hall explained very well in his talk, that relaxing measurement independence assumption. So in 2010, he wrote a PL paper where he showed that even there can be a local deterministic model for singlet correlation, provided one relaxes the measurement independence assumption. So this kind of study gives new insight in understanding applications of quantum entanglement, as it was shown in Professor Hall's talk, that how it is important for in cryptographic application, and of course in understanding the foundational aspects of Bell non-locality. So even though some remarkable results have been discovered, I just want to highlight that research along this direction is still in very early stage and has a lot of open problems. One of the difficulties is that with auxiliary Bell inequality approach, the problem very fast become intractable, even with small size input. Yeah, I think I will thank you for listening, and I'll be happy to answer if there are any questions.
Ashu, are you through?
Yeah. Yeah.
How about questions or comments?
Yeah.
See, Ashu, I have a question.
Yeah.
This PR box correlation, has it been simulated through any kind of system?
No, it is actually unphysical, because with quantum state measurement, one cannot. But as I showed towards my last slide, that if one allows communication, one C-bit, then one can simulate. But then it loses all its charm and power.
No, I mean, what I was thinking, like, for example, this this kind of gravitational models, where you have the time travel kind of thing, right? Those kind of things can be simulated on a quantum simulator in the presence of these time-like curves. Is it possible to have this? Because they have additional correlations built into them.
Yeah.
Or even like CT symmetric quantum mechanics, where there are additional correlations present. Is it possible to use them to simulate this kind of thing? People have not attempted it.
Yes, like, yeah, if it like, it will be like a big discovery. Like, if it happens in, like, first of all, it has to happen like experimentally, because then it would because quantum theory, quantum mechanics, with quantum mechanics, one can not go to PR box.
Sure.
So if it happens, means it would mean like we are finding now exceptions to quantum mechanics. So
Yeah, like for example, otherwise it will be like, this closed time-like curves, brings in contradictions, which has to be, somehow made compatible with quantum mechanics with additional conditions, those kind of things. Or maybe closed time-like curves could be on physical. It can go both ways.
Yeah.
So I was thinking of using this closed time-like curve or even symmetric quantum mechanics, there are additional correlations to see if this can be simulated. Okay, so any more questions or comments, please?
So I don't see any question in YouTube chat box. And
okay. So then, so take care. Then Asu, thanks a lot.
Okay, thank you, sir.
Thanks for giving the talk, and keep in touch. Do well.
Thank you.
Okay. Yeah, every time this thing I did, just